guys, Miss Kulkarni here. So in couple of videos earlier, we talked about how Proton NMR works and we solved some problems. In this video, I want to challenge you with one more problem. And I'm pretty sure you're going to say after that, you got it. So here's our problem. This is an alcohol and the molecular formula for alcohol is given to you as C4H10O, carbon atom number 4, and alcohol. Does that ring the bell? What kind of alcohol is that? What's the name? It will be butanol. And we need to find out, first of all possible isomers which we have for this alcohol. And in the question, we are given two different NMRs and we have to find out which isomers correspond to those NMR. So before we move to NMR, let's find out our isomers for this butanol. Remember, the molecular formula has to account for all those atoms for carbon, hydrogen, and oxygen. So here we go. So there you go. We got all those 4 isomers and look at the OH group position, location. That's a different place. Now, can you actually label each of the alcohol? Let's try it. Alright, there we go. So we got all the names, IUPAC names for the isomers of our butanol. Now next job is we have to find out which isomers are matching these NMR spectrum. So we have 2 spectrum given. One of them has 2 peaks and the other one has 4 peaks. And of course, the more details are given about the integration ratio and also the chemical shift for all the peaks there. But the most important part is how many peaks we got. So let's go back to what we got over here. So let's look at our compound A, isomer A, and how many peaks we can possibly get. These all hydrogen atoms, CH3 group, they will give you 1 peak. Then there is CH2 group, that's another peak. That's your next one. And another one, and of course OH group. So how many peaks is that? That comes out to be 5 peaks. And both spectrum 1 and 2 do not give 5 peaks. So A will not be an option for us. Let's look at compound B, isomer B. And that's our first peak. Then there is CH2. Then there is another hydrogen, another CH3, and this one. If you count how many peaks you get, you again end up having 5 peaks. So that unfortunately also will not be matching with spectrum 1 or spectrum 2. So our best bet is going to be compound C and compound D. These both isomers should be giving us matching spectrum. But which one matches which spectrum? So for compound C now. Look at carefully, this carbon atom is connected to 2 methyl groups. So these 2 methyl groups are kind of symmetrical. They're hanging off the same carbon atom. So they're going to give 1 peak corresponding to 6 hydrogen. Then this hydrogen will give you a second peak. Then these 2 hydrogen atoms are connected to same carbon. That will be 1 more peak and of course OH. How many peaks is that? That comes out to be the 4 peaks for the spectrum. Now remember, we are talking about the NMR spectrum, which is not that much of the high resolution, because if that spectrum is quite high resolution, you may end up having a little bit more doublet and a little bit more splitting pattern for all that. So for the information provided to us, spectrum C is going to give you 4 peaks. Let's see what about the compound D. And compound D has, if you look carefully, this all CH3, 3 methyl groups corresponding to 9 hydrogen atoms. They all are kind of symmetrical. They're hanging off the same carbon, like fanning around that carbon. So they will give one peak, and then there is OH. So this is going to give you 2 peaks. So let's confirm our structures matching the NMR spectrum. So spectrum 1 has 2 peaks, and that was our compound D, which was giving 2 peaks. Let's write down the structure one more time so we know if everything is matching or not. And that was your OH group over here. So all these methyl groups corresponds to 9 protons, 9 hydrogen, and OH is 1. So that matches with the integration ratio of 9 to 1. So we are good with this. We are good with 2 peaks. Now let's confirm with the chemical shift and also the splitting pattern. So we have 1 peak as a singlet at 1.3. Which one is that? Definitely that will be the methyl groups that's going to give singlet at 1.3. And there is a singlet at 2 ppm. That will be definitely an OH. OH usually gives a singlet, and that falls within the range for a OH group. So there we go. We confirm that structure D for the isomer is matching with spectrum 1. Now you know that means the structure C will be matching spectrum 2. But let's confirm one more time. Okay, so that's the structure of our compound C. Let's look at the integration ratio. We got 4 peaks. Definitely we confirm that. And the ratio is 6 to 1 to 1 to 2. So these 2 methyl groups are hanging off the same carbon atom. So they will give 1 peak, which will correspond to 6 hydrogen atoms. The next one is the hydrogen which we got over here. That will give you a peak corresponding to 1. Then we get these 2 hydrogen. That will give you 2 protons. And of course, OH group will give you 1 H. So what's the ratio? That comes 6 to 1, then to 1, and to 2. So we are good. We got the integration pattern correct too. Let's confirm with the chemical shift and also the splitting pattern. So we got for 0.9 ppm, we got a doublet, and that corresponds to actually the 6 protons. Which one is that? That's going to be the 2 methyl groups. Why it is appearing as a doublet? It's coupling with the hydrogen which we got over here. Then look at this hydrogen atom over here. It's going to couple with the methyl groups and also the H atoms on the neighboring carbon atom. So that is going to be a multiplet, and 1.7 ppm looks like a right shift. Then at 2.1 ppm we are going to get singlet. That has to be because of the OH group. And then at 3.4 ppm we get a doublet. So what's the doublet going to be? The doublet will be because of these 2 hydrogen atoms, and they will be pairing, coupling with the next hydrogen atom there. So that concludes that we got the right structure there. Now here's the deal. We use the peaks, their chemical shift and their splitting pattern to confirm the structure. The main important part here was number of peaks. That helped us to narrow down which will be the compounds matching. Then we also looked at the integration ratio. Those are simple, easy things to look up in any NMR spectrum or for any given compound. And then always when it's time to confirm the structure with respect to NMR, then you can look at the splitting pattern and also the chemical shift. But other than that, this was a good, easy question. So we know now out of those 4 isomers for butanol, we were able to figure out which one are matching with our 2 NMR spectrum. Now, as a synthetic chemist, when you do reactions, you'll always end up having multiple products. Plus, sometimes we end up having different isomers. So it is critical to identify the structure of the compound which you obtain from your reaction, and proton NMR plays a very important role. So guys, I hope you enjoyed the video, and I will see you again in next video. Until then, bye bye.